It's okay. So welcome all at our weekly TCS seminar at Jagiellonian. Today our speaker is Pat Morin from Carleton University in Ottawa. So I just checked your publications list, and I can report that the word planar or planarity in one case occurs 14 times. So we share the interest in combinatorics of planar graphs, specifically structural type results. And I think you combine it often path with algorithmic results. I know that you have interest in data structures. So it's a safe guess that we will see some good mixture of all of this today. So welcome. We are very glad that you have agreed to speak at this seminar, and the floor is yours.
Thank you, Piotr, and thanks for the invitation to speak here. I'll talk today about a couple of results with this group of authors. That's Vera Dujmovic, Fabrizio Frati, Daniel Gonçalves, myself, and Gunter Rota. So the title of the talk is Free Sets in Planar Graphs, and I'll tell you what free sets are shortly. But first, let's look at a couple of related notions. So this is just a picture of an embedded planar graph drawn in such a way that that none of the edges cross each other. So it's the sort of thing we're used to. Notice that the lines are not the edges are not necessarily straight lines. So you take some subset of vertices of this graph, and if you can find a Jordan curve that has two properties. One is it should not be a cycle in the graph, so it shouldn't just follow along edges of the graph. It should contain the vertices in this set, and it should intersect each edge either not at all. It should contain the whole edge, or it should intersect the edge in exactly one point. Okay. Then that thing is called a proper good curve, and it contains this set of vertices. Okay, so there are sometimes sets of vertices in an embedded planar graph that you can catch this way with a proper good curve. Those are that's all I want to say about those. And this definition of proper and good is basically saying that the curve behaves, so the curve in the way it interacts with the edges behaves the way that a line behaves when it interacts with line segments. So then it's natural to look at a similar definition. You take a set of vertices in your graph and some line, your favorite line, maybe the x-axis, and you ask, does this graph have a drawing? But now it's going to be a straight line drawing, so a Fairy embedding of your graph, where all of those vertices end up drawn on that line. And if you can do that, then that set of vertices is called a collinear set. So this is two drawings of the same graph, and those originally highlighted vertices are all drawn on a line. So that means that these are a collinear set of vertices. That's what we call them. If you want to make it a little bit harder, I can say take those vertices and draw them not just anywhere on the line, but at a fixed specified locations on the line. Okay. So here, can you draw this graph with those vertices at these locations? And the answer is yes, in this case. And if it's possible to do that for a set of vertices, if it's possible to do that regardless of the locations, the choices of locations that I give you, then that thing is called a free collinear set. So not only do they have to live on a particular line, but they have to go to exactly specific locations. And then finally, well, why stick to a line if you give me this set of vertices and I take any set of points in the plane and ask you to draw that graph with straight line edges so that those vertices land on those points. If you can always do that, no matter which set of points I give you, as long as it's the right size, then that's called a free set. So seems like these things are getting harder and harder, or more and more difficult. So this is sort of the hierarchy here of the pictures, starting with this proper good curve containing the vertices, and then the line, putting all the vertices on a line, then putting all the vertices at specific points on the line, and then being able to put the vertices at specific points anywhere. And it's clear that these are getting harder because if I can, for instance, draw the vertices on any set of points, then I can certainly draw them on a particular set of points that happens to be on a line. And if I can draw them at a specific set of points on a line, then I can certainly draw them on a line. And if I can draw them on a line, well, I can treat that line, sort of part of that line, as part of a curve, and then just close it up to get a Jordan curve that is actually a proper good curve that contains those vertices. Okay. So, any questions from the audience at this point? Okay. So the first part of my talk is about what I'll call the equivalence theorem. It's done with all the co-authors listed on the front page there. And this talk is a little bit of an advertisement for workshops because sort of both parts of the talk came from workshop work. This was a workshop in Barbados a few years ago. So the theorem, as you may guess from the name of it, says actually all of those four conditions are equivalent. If there's a proper good curve that contains S, then S is a collinear set. I can draw it all on a line. If I can draw it on a line, I can draw it anywhere I want on a line with any particular positions on a line. And if I can draw it with any particular positions on a line, I can draw it with any particular positions in the plane. Okay. So these are not different. In fact, they're all the same. Okay, so before I talk about the proof of that, of the various parts of that, which actually goes across a few years of work by various people, I will just motivate this maybe, although maybe motivation isn't needed. So why is this something we want? Well, this last characterization, taking a set of vertices and being able to draw them anywhere and then draw the rest of the graph around it, turns out to be useful for a whole bunch of problems in graph drawing. So initially, the problem that I studied was untangling, but there's these various models of graph drawing, column planarity. It's a question of universal point subsets and partial simultaneous embeddings, where these free sets are just very useful in solving these problems. In fact, these problems sort of reduce to finding large free sets. So large free set is a useful thing to have. On the other hand, if you want to find large free sets, it is much nicer to be able to work in some combinatorial structure than trying to directly work with the geometry of planar straight line graphs. So this first characterization is useful then for being able to show the existence of such large free sets. Okay, so let's look at the equivalence of proper good curve that contains your points and being able to, your vertices, and being able to draw those drawing of the graph with those vertices on a line. And I kind of alluded to why this is maybe sort of a natural thing to consider. just because the definition of proper good curve is basically the curve interacts with the edges the same way that segments interact with a line, suggests that maybe it's not too much of a stretch. And that's a result of Dell'Ozzo, Dujmovic, Frati, Michdlitz, and Roselli that says that these two things are equivalent. And I want to sketch the proof of that because it'll highlight the real difficulty in this, one of the big difficulties in proving the complete equivalence.
So I have a quick question.
Yes.
So when you gave a definition of the first definition of this curve,
yeah.
you had you excluded one thing, yeah, that the curve doesn't go along the cycle itself or something like that.
Yes. So the curve should not be completely contained in a cycle in the graph.
And then clearly you wouldn't be able to draw the cycle on the line, right?
That's
so
right.
That's I see. Yeah. Okay.
So, or if you like, the curve has to have some point inside of a face. It just can't be. Yeah. Okay. So this is what the proof looks like. You have this this embedded planar graph and this proper good curve. The first thing to do is to look at the edges which cross from the inside of the curve to the outside of the curve and put dummy vertices there. Next, you take the parts of the curve that are not already edges in your graph and just put edges between the consecutive vertices there. And then you triangulate, add edges to make the inside and the outside maximal planar. So you triangulate this thing. So the curve, this naturally now has a graph that's inside the cycle and outside the cycle, which you can work on independently. And one last thing is you should add one extra vertex on the curve in that place where there was no edge before. Okay. So you've got this cycle in your graph. There's a triangulation inside it. There's a triangulation outside of it. And Tutt's convex embedding theorem says that, well, if I focus on the part that's inside this cycle, there is a straight line embedding of it. And more than that, I can actually prescribe where the vertices of the cycle go, as long as on any convex polygon. So in particular, I can take the convex polygon, which is a triangle with one of its edges subdivided. That special vertex that I introduced is one vertex of that triangle. And all the other vertices, they are on one edge of that triangle. Okay. So I get a straight line drawing of the inside, and all the vertices on this curve are on one line. And then, of course, I can do the same thing on the outside, but this time I'll insist that the drawing go below the line. Okay. Now you take away all of the stuff that you had introduced. So that means when I introduced dummy vertices on the edges here, take those away and merge the edges and take away any extra edges or vertices that were added, including the square vertex. So what you're left with is a drawing of your graph, which is almost what you want. It's almost a straight line drawing. The only issue, the only edges which are not drawn as straight lines are those which happen to cross from the outside of the curve to the inside of the curve. Those things are actually drawn as two line segments. Okay. And now you appeal to actually a couple of old results in graph drawing that say, if you have a drawing of your graph in which all of the edges are y monotone curves, then meaning that a horizontal line intersects them in only one place, then you can adjust just the x coordinates of vertices in order to get a straight line drawing. So that last step, adjust the x coordinates of the vertices, and now everything is a straight line drawing. And in particular, those original vertices on this line, on the curve, all lie on a line. Okay. So the thing I want you to note here is right up until that last step, there was complete control over the locations of these vertices. The Tut's convex embedding theorem lets us choose those locations exactly. It was just in the straightening of the edges that crossed from the outside to the inside that suddenly we lost that control. Okay. So somehow these edges that cross from the outside to the inside, they're the problem. They make this problem harder than it would be otherwise. Okay, so that shows that on this bottom picture here that this first two things are equivalent. The last two things, it's actually quite easy to see that they're equivalent. So that is, if I can prescribe the locations of those vertices on a particular line, then actually I can prescribe the locations of those vertices anywhere. And the way to do that is just look at only look at the x coordinates. So you give me the graph and the vertices, you want them to go, those vertices, the points, you want those vertices to be mapped to these particular points. Just look at the x coordinates of those points and ask to draw them on a line with the correct x coordinates. Okay. And if this is a free collinear set, then you can do that. That's the definition of this thing. So I can get a drawing where all the x coordinates are correct and all of the vertices in my set lie on a line. And now you cheat and use this trick that, well, planar straight line drawings, they make a kind of open set in the sense that I can adjust, I can move vertices by very small distances in any direction without introducing crossings. And in particular, I can move each of the vertices which is on the line up and down by at most epsilon for some epsilon without introducing any crossings. So what I do is if I would like a vertex to go to position y, I move it to position epsilon times y. And if epsilon is small enough, this doesn't introduce any crossings. And now you cheat and say, okay, now I scale the whole drawing by 1 over epsilon, and suddenly that vertex, which is at position epsilon times y, moves exactly to y coordinate, to its desired y coordinate. So that's actually kind of easy. So the only thing missing is the equivalence between these two middle things, that if I can draw them on a line, I can draw them at prescribed locations on the line. Okay, so yeah, this is the main result in that paper, that S is a free collinear set. This should say F is a collinear set if and only if it's a free collinear set. All right. So now, unfortunately, because I'm mixing two slide decks, I'm going to try and draw these instead of on a horizontal line. I will try and draw them on a vertical line. Sorry about that. So let's, I'll try and sketch the proof of this. It's long, technical, but I'll try and get the main ideas across. So first thing that I'll sort of reiterate again, so the hard part comes from edges which cross from the inside to the outside of your proper good curve, or if you already have a drawing in which those vertices are on a line, then it's the edges which cross that line that are the source of difficulty. So see this picture on the left, for example. If I want to adjust the positions of those vertices which are on that vertical line, there's a sort of a lot to take care of because of those edges that cross. If you look at the picture on the right, it's actually fairly easy to move those vertices around and adjust the rest of the picture. Kind of because, well, just like the proof that I showed you, the left and right hand sides are independent. Everything you can fix one and then fix the other. Okay, so if that's the hard part, let's first study the hardest part, which is trying to make edges of our graph cross the line exactly where we want them to. So we make the problem harder. Instead of saying that vertices have to be at specific locations on this line, we'll say that the edges which cross the line have to cross at specific coordinates. And well, what would be the hardest instance of that? Well, the hardest thing would be if all of the edges crossed. So every edge is constrained to pass through a specific point on this, this vertical line, which may as well be the y-axis. Okay, so if all the edges cross this line, that means the graph is bipartite. And if there's as many edges as possible to make the problem as hard as possible, that actually means the graph is a quadrangulation. So every face of your graph is a quadrangle. It has 4 sides. All right. So this picture down here shows the setup for this sort of hard, what I think is the crux of the problem. You give me a quadrangulation. You give me which is it's drawn currently in some way so that all of its edges cross the y-axis, as in this picture. And you also give me a sequence of y coordinates, and you say, I would like edge number 1 to cross the y-axis at y coordinate 1, edge number 2 to cross at y coordinate 2, and so on for all of the edges in this graph. Okay. And you do a little more than that for technical reasons. You even tell me what the outer face has to look like. So you basically tell me the positions of the 4 vertices on the outer face. And of course, that has to be consistent with where you asked me to place the uppermost, the bottommost, and these 2 sort of central ones. And so this is what I think is the hard part. Okay, so how do we tackle this? Well, if you just use Euler's formula, you'll deduce that if you have n vertices in this quadrangulation, you have 2n minus 4 edges. And if you think about, okay, if I want to specify this drawing, you've already told me where the edges have to cross the y-axis. So in order to specify the drawing, it's enough for me to tell you the slope of each edge. So I know where it crosses the y-axis, I know its slope, so I know what line it's contained in. And every vertex is incident to at least 2 edges. So if I know the 2 lines that contain those 2 edges, I know exactly where that vertex has to be. It's at the intersection of those 2 lines. Okay. So a solution to this problem is just the sequence of slopes of those edges that cross. Okay. And now if you look at 3 edges that are incident to a common vertex, you have some constraint, which linear constraint, which basically says that the three lines defined that those edges are contained in have to meet in a common point. It has to be the vertex that they're going to meet at. Or more specifically, they have to meet at some common point. That point will be the vertex. So there's a constraint from these things, a linear equation. And now, so for each vertex, you pick two edges, and you use this equation for each other edge incident to that vertex. And what you find out is that you get m-4 linear equations this way. So we have m edges, and that means m slopes to provide, to solve for. But actually, don't forget, there were those 4 edges on the outer face. Their slopes are already defined. So we get a system of linear equations which has exactly the right number of, the same number of variables as constraints. So yeah, the situation looks good. It looks like this thing could have a solution, and what is even better, maybe it has a unique solution. Right, so that's this picture. It looks promising. Does it have a solution? Does the solution give a Fourier embedding? The answer to both of those questions is yes. I'm not going to show you the proof today. I will just say that it is not like other proofs that I've seen. So basically, it uses the fact that there is some drawing in which all of these edges cross the y-axis, which means there is a sequence of y coordinates for which, if I use those y coordinates, I get a system of equations that does have a solution, and it gives me that drawing back. And then you use basically a deformation of those things. So you take each of those y coordinates, the ones that you know work, for which this thing has a solution, and you linearly interpolate. And now you hope and pray that as you do this, right, the system of equations is changing continuously, and you hope that it continues to have a unique solution the entire time. And indeed it does. So how do you show that? Well, what you do is you look at the determinant, you look at the various things that could cause the determinant to become 0, which would mean that the thing doesn't have a solution or it has a non-unique solution. You look back at what that means for the graph, and you show that those things don't actually happen in the graph. Okay. So so that seems to be handle the crux of the problem, where you give me a quadrangulation in which all the vertices or all of the edges cross the y-axis, and now I can tell you exactly, I can give you another drawing of that thing where all of the edges cross at specified locations. It's not hard to get from there. So that's an example which actually seems quite far from what we want for collinear sets, in the sense that we want vertices on the axis, not edges. But it's not hard to get from there to a situation where you talk about something that's like a quadrangulation. In fact, it's related to a quadrangulation, but it's what you get when you take a few of those edges that cross the axis, an independent set of them, and contract them so that the corresponding vertex lies on the y-axis at a specific location. All right. So that thing has a name. I think we call it an A graph in the paper. So it's a quadrangulation with some of an independent set of edges contracted. Okay. All right. So how do we get from the real problem? So the real problem is we have a planar graph. We want to put some set of its vertices at specific locations on the y-axis. And what we know is that some set of its vertices can be drawn somewhere on the y-axis. We want to get to something that looks like this quadrangulation. So there's a long statement of this technical theorem here. But basically, the theorem says we can do this, and not only can we do it, but we can also control to within epsilon exactly where the edges cross the y-axis. Okay, that's nothing. This is basically an inductive proof that needs a stronger hypothesis, which gives us control over the positions at which the edges cross this axis. And it's induction on the number of vertices plus the number of edges that don't cross the y-axis. And from this point on, it ends up being more graph theory and less geometry, less linear algebra. So the linear algebra is over. Now it's things that probably most of us are more comfortable with. And it uses a few types of reductions. If your graph has separating triangles, you'll do induction on those, on the inside and the outside separately. If you have edges that don't cross the axis, you'll be able to contract those. Or you'll be able to flip them so that they do cross. Edges that are contained in the y-axis, you flip those so that they become edges that cross. And then finally, if there's none of those things is possible, you have one of these graphs which is simple enough to apply this theorem for these quadrangulation-like things. So just quickly run through some of the reductions. If my graph has a separating triangle which crosses the y-axis, so it intersects the y-axis or the proper good curve, since they're the same thing now, I first remove the contents of that separating triangle, inductively get a drawing which does what I want, and that separating triangle is now a face in that drawing. And then I take the inside of that separating triangle, inductively get a drawing that I want, which has a prescribed outer face. That was one of the conditions of this inductive theorem. And then I stick it back together. So that's separating triangles. They're, as usual, they're easy. Edge contractions. Well, if I have an edge which is completely, so it doesn't cross this this line that I'm trying to draw things on, and not only does it not cross, but the two triangles incident on that edge don't cross, then I just contract that thing, apply induction, get back a drawing, and then do a very small uncontraction. Okay. And it's actually this uncontraction thing that says you can get arbitrarily fine control over where the edges cross, but not perfect. There's a small epsilon in there. So that's for edges which are on one side of this line, and not only is the edge, but the two faces are also on one side. Now there's other kinds of edges, ones that live on one side, but the two faces don't live on one side. So up top is one example. Here you see this, there's a blue edge. It's on one side of this curve, but one of its faces crosses over the curve. And there's more to this picture. And actually this picture is specific to this case, that one of the triangles incident on that edge lives entirely on one side of the curve, but the two triangles attached to that are actually on the other side of the curve. When that happens, it's safe to flip that edge, apply induction, and what you're certain about is that in the embedding that you get inductively, the two faces incident to that edge form a convex quadrilateral, which means you can flip this this edge back to what it should be to get the drawing you want. There's a second such case where it's not quite so clean, but it's another example where it's safe to do this flipping operation, to take an edge which is on one side of this thing and flip it so that it actually crosses, and be guaranteed that when you return, you'll get a convex, that edge will be have two faces adjacent to it, which form a convex quadrilateral, and you can flip it back again. Okay. And then there's edges that are actually on the y-axis. You just flip them and now they cross the y-axis. There's no difficulty there. All right, so finally you do all of this. There's no more separating triangles. There's no more of these contractible edges, none more of these flippable edges, and there's no edges in the y-axis. And then you can argue that if you have an edge which does not cross the y-axis, that still remains after doing all of this, then its two incident faces cross the axis. Okay, so if you think about that's saying that I have an edge that lives on one side of the y-axis, but both its incident faces cross the y-axis. If I take all of those edges away, so when I take one of those edges away, I get it, those two triangles become a quadrangular face, all of whose edges cross the y-axis. And if I do that to all of those edges and take them away, I have only quadrangular faces that cross the y-axis. Okay. And well, and then finally, there's the vertices that are on the axis, but actually those are handled by this extension to the quadrangulation theorem. So you apply this result for quadrangulations and finish there. Okay. All right. So that's the sketch of the proof, which is basically from your triangulation, do everything you can to reduce it to the hard core of the problem, and which is basically a quadrangulation whose edges must cross the y-axis at specific locations, and then solve that using linear algebra. All right. So would anyone like to ask me a question now?
So is this statement with arbitrary precision, doesn't it disturb you?
No, so the statement says the vertices go at exactly where you want them to. The edges go within intervals of size epsilon that you pre-specify. Okay, and that's, you just need that. I mean, you need that strengthening in one of the induction cases, just to make sure you don't do something silly like have an edge pass to the wrong side of a vertex, right? So there's basically only one embedding of this thing. The y-axis intersects vertices and edges in some specific order. I need to make sure that that order is preserved for the vertices and the edges, which requires you to be able to say something about where the edges cross. You can't specify it exactly, but you can say that it's between two particular vertices. but the vertices themselves go exactly where you want them to. Other questions? Okay, so that finishes that completes the picture here, showing that this 2 and 3 in this theorem are equivalent, or 2 implies 3 if you like. So 1 implies 2, implies 3, implies 4, and 4 goes backwards easily to any of these other ones. Okay. So the moral of all this is, if I want to find a large free set, which seems like a very flexible set of vertices in a planar graph, it's enough for me to find a proper good curve that contains that set. So take your favorite embedding of the graph and then find a proper good curve in that embedding that contains that set, which is really a combinatorial problem now. It gets away from algebra and geometry. Okay, so the second part is about finding these large free sets, or more precisely now, it's about finding proper good curves that contain a lot of vertices. Does anybody recognize this picture? It's a picture of where this work was done. Yeah, Piotr knows. So this is work that was done at a workshop in Poland. A nice palace in a town that I won't try and pronounce the name of, and this is where I met Piotr. Okay, all right. So a little bit of background. Great. So these free sets are good. Do they exist? Are there large ones? Well, one thing I can tell you for free is every planar graph has a free set of size 3. Right, that's just 3 vertices. And that's just because, well, for any 3 vertices, any 3 points, there's an affine transformation that takes them onto any other 3 points. So take any 3 vertices of your graph, you can map them to whatever you want and preserve the non-crossing drawing. So that's a little bit too easy. But back in 2009, when we weren't even thinking about really about free sets or collinear sets, we were thinking about untangling, which is basically asks, if you give me a non-planar drawing of a planar graph, how many vertices do I have to move to make it planar, or how many vertices can I leave fixed? We showed that every planar graph has a free set of size at least square root n, or some constant times square root n. The proof of that is by what is called the canonical ordering of planar graphs, or canonical ordering of triangulations. But as soon as that was seen by people who do Schniederwoods, they saw immediately that actually you can do the same thing with these Schniederwoods. All right, so there's a lower bound of square root n on these things. What about an upper bound? Well, there's a result or observation even of Ravsky and Verbitsky, who were the first to study collinear sets, that, well, there's an upper bound of n to the log base 23 of 22, n to the 0.9859. And that comes, we will see, from specific kind of graphs that do not have long cycles. Okay, So back to proper good curves in embedded planar graphs. We can forget about all this other stuff now. So if you give me one of these proper good curves that contains, let's say, k vertices, then take a little deformation of it so that it doesn't contain any vertices. So, if it passes through a vertex like this, in one face incident to that vertex and out another one, just have it walk around the vertex instead. Okay. Now it doesn't contain any vertices. It's still a proper good curve. You can check that, the fact that, so the definition of proper good curve actually says that, the definition of proper good curve basically implies that. The danger would be if the curve contained two vertices on the same edge, there would be a problem, but the only time that happens is when the curve contains the entire edge. So little deformation like this, you get a curve that contains nothing. And actually, if you think more about the definition, if this thing is if your graph is a triangulation, you see that this just gives you a cycle in the dual graph. So the dual graph is the one that has a vertex for each triangle in your triangulation, and an edge between two triangles if they share an edge. And so, that curve, just look at the triangles that it intersects and the order that it intersects them. And you'll see that actually gives you a cycle in that dual graph. Okay. So if you have a long proper good curve, where long means it contains a lot of vertices, well, you get a long cycle. And that's interesting. And you might, the natural question to ask is, can you go in the other direction? If you just give me a long cycle in the dual, can I turn that into a proper good curve that contains a lot of vertices? That would be great. And the reason that would be great is cycles in these dual graphs have been studied a lot. So if a long cycle in the dual graph gives us a proper good curve containing many vertices, we would be very happy. So from this point on, our graph is a triangulation. Adding edges only makes the problem harder. It will have maximum degree delta. And when your graph is a triangulation, your dual graph is a three-connected cubic planar graph. And the bound on the degree of G gives a bound on the size of the largest face in the dual graph. And that's important. These things are three-connected and cubic. So the longest cycle in this dual graph, or the longest cycle in any graph, is called the circumference of the graph. And the circumference of three connected cubic graphs actually has been studied for a long time, both planar and non-planar. If you go way back to 1884, actually, Tate conjectured that all of these three connected cubic graphs are Hamiltonian, in which case they have a cycle of length n. That turned out not to be true. Tut disproved that with a 46 vertex example whose longest cycle had length 45. And I think there were two improvements, but the best still, I think, is Grunbaum and Walter, who show, and this is a 23 vertex graph with no cycle of length longer than 22, which, if you use that as in a recursive construction, means that the longest cycle has length n to the log base 23 of 22. So that's for the lower bound side. That's where it ended, the year I was born. In terms of upper bounds, those have been growing. In 1966, Barnett showed that any one of these three connected cubic graphs has a cycle of length at least log n. Bondi and Simonovitz showed that, well, you can do better than polylog, but not quite polynomial. Jackson gave a very strong result that you can do better than polynomial. I mean, you can do polynomial and even better than root n, so n to the 0.69. That moved up to the n to the 0.75. And the record, the last time I checked, is n to the 0.8. Okay. These are, I mean, these are all, each one of the last three, it takes some work. It's not easy stuff. And we'd like to leverage that. Okay, so in particular, these graphs, three connected cubic graphs, have cycles of length longer than root n, which is the current record for the size of free sets. So root n is the largest free set we can guarantee. These things have longer cycles than that. So if we could turn those cycles into free sets, we would be very happy.
So what are the proof
yep.
what are the proof techniques for these lower bounds, for these recent lower bounds?
They're inductive reductions.
It's like discharging or not?
No, so at some point I looked through the Yu and Zhang paper, hoping that I could use it directly to find what I was looking for. And they're sort of, no, that you find cut sets of size 3 induct on find a long path on the inside that enters and leaves through the cut set, find a long path on the other side which enters and leaves through the cut set, and combine those two things basically in clever, complicated ways.
Okay, thanks.
Okay, so yeah, can you, does this work? So if you give me a dual cycle, that's definitely a proper good curve. It only passes through edges once, and it, yeah, I mean, it just is a proper good curve, but it doesn't contain any vertices, so that's not helpful for us. It doesn't give us a proper good curve containing many vertices. But maybe we can just take one of those long dual cycles and bend it so that it contains some vertices. Can we do that? Well, sometimes we can and sometimes we can't. So on the left here is an example where we can. So there's a dual cycle, there's this vertex U, it passes through its neighborhood, it enters that neighborhood of U. By neighborhood, I now mean the faces incident to U, stays in there for a while and then leaves. Well, we could skip all that stuff in the middle and go straight through U and enter and then leave, and have now the curve pick up U and along the way. That's great. So that works. But over on the right is an example where it doesn't work. If we try and do that here, well, there we pick up U the same way we did before, but now we have a problem because now the curve passes through U, but it also intersected an edge incident to U. So now it intersects that edge in two different points. And that's not allowed in a proper good curve. So that's an example where we're not allowed to do that. And what's the difference between these two pictures? Well, the difference is in one case, the curve so if I look at this face in the dual that corresponds to U, the curve intersects that face in a path. And in the other example, the curve intersects that face in two paths. So the part on the left seems like a good situation. On the right, not such a good situation. Okay. So that's where these definitions come from. So now we're dropping the triangulation. We're going to forget about it. We're just going to look at the dual graph, which is a three regular, three connected planar graph. And so that thing has faces. You can forget that they happen to correspond to vertices in the original graph. And we have a cycle in that graph. And we'll say that the cycle touches a face if it uses one of its edges. And since this thing is three regular, if it uses one of its vertices, it actually has to use one of its edges as well. We'll say that it caresses a face if its intersection with that face is a path. Remember, that's the good example, somehow the example that's helpful when we can pick up the vertex this way. And it pinches the face if its intersection with that face has more than one connected component, or if it, in a boring degenerate case, if the cycle is the entire face itself. That's just an edge case. So here's a picture of a three regular planar graph. The red thing is a cycle. There are pink faces. Well, so there are white faces which are not even touched by this curve. We forget about those. There are pink faces that are touched, but they're actually pinched by the curve. So if you look at each of these pink faces, the curve visits the face for a while, goes away, and then comes back and visits the face again later. That's pinched, that's not good. And then each of these green faces, those are caressed by this curve. The curve comes along, touches them, walks around that face for a while, leaves, and never comes back. So these green faces, the ones that are caressed, those are the good ones. And just so you can remember what these variables are: tau for touched, the number of touched faces; rho for the number of pinched faces; and kappa for the number of caressed faces. And of course, if you touch a face, you either pinch it or caress it, so you have this identity. Tau is touched is equal to pinched plus caressed. So here's an easy theorem. If you give me a curve that caresses kappa faces, then I can, so not a curve, but rather a cycle that caresses kappa faces in this dual, then I can convert that thing into a proper good curve that contains at least kappa over 4 vertices. And that is just by doing exactly the trick that I showed on that earlier slide of bending the curve so that it goes in and picks up a vertex. The only thing you have to be careful of is the faces that you do that on. They have to form an independent set. Otherwise, if you do that in 2 different locations, you might cause the problem again. So you might not be a proper good curve anymore. The good news is that the graph, which is consists of the caressed faces, the vertices are the caressed faces with an edge between them. If they share an edge, well, that's a planar graph. So it has an independent set whose size is at least 1/4 of its total size. So as long as you do this with an independent set, no problems occur. You pick up all of the vertices from each of those caressed faces in the independent set. Great. So, we if you give me a cycle in the dual that caresses a lot of faces, then I get a proper good curve that contains a lot of vertices, and that gives me a free set, since proper good curves, the vertices contained in the proper good curve, those are the same things as the vertices of a free set.
So we used here the assumption that you look at the caressed faces because where you say that it's planar, right? If it would be pinched, then the adjacency graph, that's the thing, or am I?
No, so if you have a face which is pinched, there's no hope of picking up the vertex in that face. So that's the example on the right here. If I deform either of these things to pick up U, then there's going to be edges which are crossed twice by the curve,
Yes,
once
yes.
at U and once somewhere else. So those are hopeless. Those are the pinched faces. The caressed faces, they're hopeful. I can do this once without any difficulty, just like I had done in this picture. The only thing to look out for is if I did this to two different caressed faces, I might cause I might pick up two vertices at the endpoints of the same edge, which would also be a problem. But it's enough then to take an independent set of caressed faces to avoid that, which is why you get kappa over 4 instead of kappa. Okay. So what we would like to show then is if you have a long cycle in G, then you have, it's not G, G star in the dual, that you get a cycle that caresses a lot of faces. Now we can't show that. We can only show that if the length of the cycle is at least kappa times some function of the maximum degree, then you can caress kappa faces. Okay. So unfortunately, the degree comes into it. So this is the theorem. If G has maximum degree delta, G star has a cycle of length L, then G star has a cycle, different cycle possibly, that caresses this many faces, L over delta to the 4 faces. Okay, so before explaining the proof idea, I would like to just show you a worrisome example. Here's a 3 regular, 3 connected planar graph. And here's a cycle in that graph. It's dark. It's this dark thing, the darkest edges in the graph. That's a cycle. And whatever, it's of length 2k or something, 2k plus 3. And it only caresses 4 faces, these ones at the end. All of the other faces, so the interior faces inside the cycle, they're all pinched, right? The cycle hits them on the bottom and then hits them again later on the top. So they're all pinched. And these outer faces, the faces outside the cycle, it's the same situation. They're all pinched as well. Okay. So this looks bad. If you give me a long cycle in your dual and it looks like this does not help at all. It means we can find it means if using this approach, we can find a collinear set or a free set or whatever you want of size 2, which is worse than the trivial 3 bound. So somehow we have to.
So that supports also your dependence on the maximal degree, yes? That it's kind of necessary.
Well, no, here the maximum degree is 6 or something, right? This is, these guys have, 6 edges. So the maximum degree is not even big here. This is just a bad cycle.
Oh, wow. Okay. Okay. Indeed.
Okay, so we have to be able to resolve this somehow. I mean, we can't just take the cycle that we are given and use that, because there are bad ones. So here's the idea. We're going to define two trees. One of them is going to be something that corresponds to what's going on inside the cycle. The other one is going to be something that corresponds to what's going on outside the cycle, T0 and T1. We're going to show that a leaf of this tree, every leaf contains a crest face. So you see that in this picture. The two trees are actually paths, and the leaves of those trees are the crest faces in this picture. We're going to have to show that the trees that we define this way are big. If you give me a long cycle, I'll get trees with lots of nodes in them. And now already we would be done if either of the trees has a lot of leaves, in which case we found a lot of crest faces, because every leaf has a crest face. So it must be the case that neither of the trees has many leaves. So both of the trees are big. They have length proportional to L, but they only have a few leaves. But that means they have many degree 2 vertices, just like in this picture, right? If a tree has a lot of nodes, but a small number of leaves, that means most of its vertices are degree 2. So that's like in this picture. And we'll call them bad nodes if in the tree they have degree 2 and there's no crest face inside that node. So this is all quite vague, and it probably will be for the rest of the talk, but that's okay. That's the idea here. Okay. All right. So there's the last step, and I think this is the clever idea, is if you have enough bad nodes like this, you'll be able to perform a surgery that increases the number of leaves or increases the number of crest faces to get a different cycle. All right. So first, defining the two trees. I'll be quick and deliberately vague about this. So back to that picture we had before. There's the cycle in red. There's the graph that we have. What's inside of here doesn't look like anything we're going to get a tree out of, because there's a mess in here. So we'll get somehow, we'll identify some edges in here which are not interesting, I don't want to say the whole definition, but we'll identify some stuff to remove in here. Or in particular, we'll take faces of the original graph and just merge them into blobs or groups of faces in such a way that, you can imagine we're sort of erasing edges in the graph. In such a way that all that we're left with now is once we do this, then the stuff inside the cycle, those blobs, they form a tree structure. So and say that, if two blobs share an edge, or actually it ends up being a path, then you say that they're adjacent, and you look at that structure that you get out of this, and you get a tree structure. So I think this picture explains it better than anything else. So you do some simplifying work inside of here, which is merging of faces, so that the thing that you get ends up being a tree. The nodes in this tree correspond to collections of faces. Some of them are quite large collections. So for example, there's this one blue node on the left here, which is actually corresponds to a lot of faces in the original graph, and some of them are not so bad. But after doing this appropriately, you get two trees, one on the inside and one on the outside. And actually, most of a lot of the proof now, you can see it coming from this picture. The first thing to show is that if you have a leaf in this tree, then somewhere in that leaf, which corresponds to a collection of faces, one of the faces in that collection is caressed by the good curve. Okay, so that's the definition of the trees. You want to show that each leaf has a caressed face. That ends up actually being easy. So imagine that this red thing is your cycle. This P here is some path that separates one node of your tree inside the cycle from the other one. The claim is that, well, in one side, R in this picture, somewhere in there is a leaf that is a node that is a face that is caressed, and it's just by induction. Either R is already, everything to this one side is already a face, or you can look at the face that contains this corner and see that if it's not caressed, then there's a smaller subproblem contained in R that's of the same type, which essentially leads you to a leaf of the tree that has a caressed face. All right, so that's great. Now the sort of cool thing that I want to show you is this surgery, which says, now suppose everything else has gone bad. I'm in that extreme case that I saw before. Each of the trees is large. There's lots of nodes in those trees, but they just don't have very many leaves. In fact, there's so few leaves that almost all of the nodes in the tree are degree 2 nodes, both of the inner tree and the outer tree. So if almost all the nodes are degree 2 nodes, then that means there's a very long path in my tree. That's supposed to be represented by this pink thing here. And not only that, so that long path in my inner tree, it's on the other, so the boundary of that thing is the cycle. And on the other side of that cycle is the outer tree. And all of the nodes around there are also degree 2 nodes. So roughly the picture looks like this. This red thing is my cycle. There's a huge path of degree 2 nodes. In the middle of that path, I pick one of those degree 2 nodes. And if I look around, even in what's happening in the outer tree, which is the blue thing, I see more degree 2 nodes everywhere. So you do a little surgery on the cycle, which you can think of as changing the colors of the nodes in this tree. So there was this node A1, which was part of the outer tree, and this node U, which was part of the inner tree. So you can imagine the inner tree is pink, the outer tree is blue. I change the color of A1 to pink, the color of these other nodes that are appropriately chosen to blue. And well, the pink-blue boundary again becomes a cycle. There's some tree associated with that cycle, but what happened here is somehow the branching went up in that tree. So now A1, which used to be a degree 2 node, is now a degree 3 node. And if you look, actually some more leaves showed up in these things. So for instance, A0 is suddenly now a leaf. We'll be able to find a caressed face in there. Okay. So you can increase the number of leaves, or you can increase the number of caressed faces. You have to do some work and a bit of analysis, but you'll always be able to do one of these surgeries to increase the number of faces that are caressed, or increase the number of leaves in your tree. One of these surgeries changes the length of the cycle. Right, the length of the cycle could decrease because you've somehow, you've changed it in some way that has to do with a bounded number of faces. Luckily, you can bound all of that change by delta. So maybe the length of the cycle went down, but it went down by at most something like delta cubed. You can get away with this large number of times before the cycle gets too short. So that's the idea. I'm not, I'll skip the rest. There's an issue of nodes in the tree being large, but I won't bother you with those. Okay, so in conclusion, if your dual graph has a long cycle, then you can find a large free set. So it's basically proportional to the length of that cycle divided by the maximum degree to the fourth. So for bounded degree planar graphs, that means that the square root n bound, lower bound goes up to n to the 0.8. And the big open problem here, I think, and because I think it's true, is to get rid of the dependence on delta. So the proof that we gave has deltas everywhere in it, but there's no reason why delta should be a problem. There's no reason that a big face or a high degree vertex should actually cause a problem. So I would love to see someone get rid of that and show that that basically free sets and long cycles in the dual are up to a constant factor exactly the same thing. Okay, and that is all I have to say. Thank you for your attention.